Hello everybody, thanks for coming. It's getting pretty hot in here, so if people still have Scala compilers running, then please shut them down. That will help a lot. I'm going to give a talk about options and futures and how to unsuck them. I'm going to introduce the problem first and then some solution. Two warnings. First warning is nothing that I do is new at all. Everything has been done for at least 5 years by people in Scala and probably much longer as well in other languages. And there's going to be a shitload of code. You don't have to read or understand anything. I'm describing the general concepts, and you can always look it up later. So let's get started. We have a problem. We want to add two numbers, but both of the numbers are optional. So we have get x, get y. They return an option of an integer. And we want to add these two. So how can we do that? We can use flat map and then make some nested structure, and we can add the x and y, and that's fine. There's a slightly nicer way, which involves a for-comprehension. So that's this option. This is exactly the same as the previous one. The latter one is just syntactic sugar for the map and flat map, but it looks slightly nicer because you don't get the nesting, and it's visual, clearer what you're actually doing. So this is really just a mechanical transformation that's just written in the Scala language specification. If you have this for comprehension, and this is the way it desugars, it's very early on in the compile phase, and it's really just a mechanical transformation. And what's interesting here is that this doesn't just work for options, it works for anything that has the necessary methods that the for-comprehension desugars to. So in the cases that I'm using, that means the objects need to have map and flat map methods. So, well, we're familiar with some objects that have map and flat map methods, option, future, list, etc. So we can use all these in for-comprehensions. So, for example, take this one, almost the same problem, except this time the numbers are not in an option, but they're in a future. We can still do it with map and flat map, but we can also use the same for-comprehension, except the result is a future of an int this time. So far so easy. What's the problem? Well, the problem that you run into these days a lot, because there's so many asynchronous libraries that return futures, is that you get nested things, nested containers, nested contexts. For example, a future with an option inside. And if you try to work with these, then you might have noticed this kind of sucks. So what we're going to see in this talk is a way to unsuck working with these things. If we would try to do a for-comprehension like we did for the previous example, then this doesn't work. Because if we write it like this, then in the for-comprehension, left of the arrows, the x and y are option of integer, and they're not integers, so in the yield they're still option of integers, and we cannot just add them. Actually, I think this compiles in Scala maybe because of the weird any to string add, but it's not what you want. Of course, there's no real issue. We can solve this. We can make this program where we want to add these two integers. We just use some more maps and flat maps. First to map the futures, and then once we've got the stuff out of the futures, then we map and flat map some more to map the options. But this gets messy. I mean, it's this messy if you have 2 levels deep, and it gets much more messier if you have more things coming out of a future or option. You can slightly improve on this in an easy way by doing pattern matching immediately. So you can write it like this, and then you avoid mapping on the option because we immediately pattern match on the none or the sum. That's the option. So what's the main issue that we have? The main issue is that we're trying to use map and flat map on a thing, but map and flat map do not work on the most inner value, so the integer in this structure. It works only 1 level deep. So if we use map and flat map on future, then what we work with is the option, while what we actually want to work with is the integer. So that's basically what we're going to solve, and the solution is not very hard. We'll just define a new wrapper. Let's call it future option. That contains one of these structures. It contains an inner value of future option A. And now we're going to implement map and flat map on this thing, but in such a way that it works on the most inner value. Then you get to the point, what is a map function? How should it look? Well, for me, that's just monkey see, monkey do. We take a look at some other map methods, for example, on list, option, and future. And you can see that they all have the same structure. A list with a type parameter A has a map function with a type parameter B, takes a function f from A to B, and it returns a list to B. For option, it's exactly the same. For future, it's also exactly the same, well, except in Scala it also takes an execution context, but we'll just ignore that for now, actually for the entire talk. But this is how a map looks on most of the other stuff in Scala, so let's just mimic that. We're going to implement on our future option A method map with a type parameter B, takes a function from A to B, and we're going to create a future option of B. That's not terribly hard. We just create a new future option, map on the outer thing, map on the inner thing, apply our function, and we're done. So, one down, one to go, flat map. How does flat map look on these existing classes from the standard library? Very similar, except the function is not A to B, but it's A to, well, the B inside the container, inside the context, inside, well, the thing. So for list, for option, for future, very similar. And looking at that, we can define our flat map. We want a flat map with one type parameter B. It takes a function A from a future option of B, because that's the structure that we're working with. And it's going to return a future option of B. Implementing this is slightly harder. It's not hard. It's an interesting puzzle, so I encourage you to try it sometime. But as you can see, the solution is not very hard. Here we have implemented flat map for our future option, and that basically completes our class future option A. It now has a map and a flat map method. And they both work on the inner value, so they don't work on the option inside the future. They work on the value of type A that's totally at the center of this structure. And given that we now have a thing that has a map and a flat map method, we can use this in for-comprehensions, because for for-comprehensions it works on anything with map and flat map, like I said. There's no trait you need to implement. There's nothing. As long as you have a map and flat map method, it will just work. So back to our original problem, get x and get y. Still return a future of an option of an int. We want to add the two integers that are in the center of these structures. So now we just wrap the future option int in our new future option class. Use that in a for-comprehension, and now in the for-comprehension x and y are integers, and we can just add them. Of course, the result that we get there is also a future option int, which is probably not the structure that you want to continue using in the remainder of your program, because, well, this is just a class that we made up, so we have to get the inner value out again. Which is easy. We just take the inner field that's on the future option class. So, basically, this is almost everything there is to it. We have an interesting structure, and we just wrap it in something that knows how to get to the most inner value. We define map and flat map for that, and then we can use it in for-comprehensions. Except the thing that we have now is very specific. It only works on this structure, future, with an option inside, but that's not the only structure that we're working with. We have values come in all different kind of shapes, so we need to see if we can generalize this a bit. So part 2, we're going to try to generalize this class, this very simple class that you could have written, into something that that's more widely applicative. So take another good look, future option. What you see here, that from the future, the value inner, we only use three things. We use map, we use flat map, and we create a new one. We just create a new future with some value inside it. So that's interesting to notice. We already things map and flat map that we could create, and now, well, for this future we also only use map, flat map, and well, we need to create new futures. So we only do three things with this outer container: map, flat map, and create a new one. So that's something that we could abstract over. So let's say instead of making this thing for future, let's say let's make an interface for this. Yeah, let's just make a trait that has a type parameter, and the type is a future. That has a map, a flat map, and a create method, and give it a suitable name. People have done that, and they said a suitable name for this is monad. So let's define a trait monad that looks like this. It has a map and a flat map method that look very similar to the ones we've defined before. The only difference is then we define map and flat map on an object, and here the object is external, so the first parameter to map and flat map is the thing that you want to map and flat map. But using this trait, we can generalize our future option class and make it an any monad option class. That's parameterized not by just the inner value type, but also by the type of monad, the outer of the stack. So we had a future option something. I call future the outer, and option the inner thing. So we've parameterized over the outer one, which is m. And then we say this thing takes a value, some m with inside it an option a. We need a monad instance for this thing, otherwise we don't know how we would map or flat map the m. But now that we have the type class for that, we can do that. And then we can redefine map and flat map to not call map on the object, on the inner object itself, but on the implementation of the monad trait for this thing. So what we would need to reuse this for futures options, we have to implement this monad trait for future. Well, you can imagine that it's not very hard to implement map, flat map, and create a new future for futures, because that's basically what we're just taking out. It already has map and flat map methods. So that's easy. So what we've got now is some sort of structure that takes a monad, and it also is a monad itself. Why is it a monad? Because it has map and flat map methods, and it has a constructor, so you can create new ones if you put a value in. And people also have given this a name. They say this is a monad transformer, because it takes a monad and transforms it into a monad that behaves slightly different. A natural question would be, hey, if we generalized over the outer container, the future, can we also generalize over the inner container, the option? Can we basically make some class, and whatever stack of monads you put in there, it will just end up a single monad, and it's going to be perfect? That's not possible, apparently. Maybe you've heard people say or read the phrase, monads are not composable, and what they mean, or this is basically what they mean, you cannot do that. You cannot make a single recipe that takes two monads and creates them into a new monad. You have to specify it for one of the two monads. So we made a specific recipe that works with any monad with an option inside, and then we can make that, but we cannot make a transformer for any monad with any other monad inside. That's not possible. We've made a monad transformer. We've defined a monad trait. It's all very easily fit on a single slide. So hopefully you feel comfortable now that monad transformers are not a very hard concept. But you don't necessarily have to define them yourself in your code, of course. We could, for example, use RAM from the Scala Z library. They have many more methods defined on them besides map and flat map. And they also provide many instances for monads. So they have the instance of the monad trait for list, for option, for future, etc., which is very useful. But they are fundamentally the same stuff as we just built. Different in the details. The one for option is called option T. So if you were ever wondering in Scala Z, the classes that end with a capital T, they're transformers, and there's a bunch of them. They call the inner value that we called inner, they call it run. So you can do my monad transformer.run, which looks nice. And the methods on the monad trait, there's also a monad trait in Scala Z, of course. They have different names. They use point instead of create, but it's the same thing. They use bind instead of flat map, but it's the same thing. And map is not an abstract method on that thing. It's implemented in terms of point and bind. You can basically, if you flat map something and you use another point or create inside the flat map, then it's the same as map. So suppose that instead of our own any monad option, we use the one from Scala Z, the option T. Then our program would look like this. Get x and get y are unchanged, but in our for comprehension, we now wrap get x and get y into option transformer, and the result of the for comprehension is an option transformer parameterized by future, the outer thing of the structure inside, and the integer, the most inner value. And again, we can get the regular structure, the future option in out, by just calling run on the option transformer. So this is how you unsuck options in futures by using existing libraries. And hopefully you're not scared, still not scared, because if you wanted, you could just write your own option T, because it fits on the slide and it's very simple. Now, other monad combinations. Option is not always the most useful structure to use, especially if you have multiple of them and you want to compose them. Well, in our example, we have get x and get y. If any of the two return a none, then the result of our computation is going to be none. And we're clueless about whether A was not there, B was not there, or maybe they both weren't there. And we cannot inform our user about that. We just say, hey, something's not there. And yeah, often when we make software, we want to inform somebody or someone or something what went wrong. And option is not so suitable for that. There's an alternative. That's the either class in the Scala standard library. But that thing is not a monad. That means we cannot do map and flat map on an either. Because it says, well, I don't know on which side I should map and flat map, because I potentially have two values inside me, a left value or a right value. No map and flat map. It's called that either in the standard library is unbiased. There's an alternative in Scala Z that's called disjunction or Scala Z either, or sometimes just either. But the class name is // which Scala allows. It has two concrete classes. That's dash // and the other way around. And they are left and right, more or less. So for the people unfamiliar with either, either is a sum type. And you could basically think of an option has a left side, none, and a right side, sum, with a value inside it. And the none is not very rich. It just means, hey, the thing is missing, but it cannot contain any information other than that. So either is sort of like the none gets replaced by something that does contain a value. For example, a string error message, or maybe an exception, or whatever. So either is really like an upgraded option where the left side or the failure case can also contain a value. Conventionally, we use the right side of this either to indicate that the value is right, because right is right, right? And the left side is what we use for error or for failure, etc. And once you've decided on that, once you set the left value is the failure side and the right value is the successful side, then it's sort of natural to say, hey, then map and flat map should work on our right side. So if we have a right and we do map and flat map, then it actually does map and flat map the value in there. If we have a left and we do map and flat map, then it doesn't do anything. Because like in the for-comprehension, the first thing that fails basically aborts the whole computation. And there's no magic in the aborting. It still goes through everything, except every invocation of map and flat map that the for-comprehension desugars to just does nothing. Because if you have a none and you do map or flat map on a none, nothing happens. On an empty list, nothing happens. And on a filled future, nothing happens. So similarly, on an either, if it's a left value, then map does nothing. So this one is biased. It's biased to the right side, and map and flat map work on the right side. So for many possible uses, this Scala Z disjunction is much more useful than the regular Scala either class. One of the coolest things about this class is that you can also use infix notation. So where you have val x is \//ab, you can also write it like this. And then it's really natural to say val x is of type A or B. So what can we do with this? For example, we have an age function that takes a name, a string argument, and it's going to return either a failure, if it doesn't know the age of the person with that name, or an integer if it does know the name. So this one only knows about my age. If we put Eric in, then it's going to return a right value, 30, so successful value that actually contains an integer. If any other name is passed in, then you get a left value with an error message. The age of this person is unknown. So if we invoke age Eric, we get a right 30. If we invoke age John, then we get a left age of John is unknown. And we can make for-comprehensions, right, because either is a monad, it has map and flat map, so we can use it in for-comprehensions. And if we make this program, for example, we try to add the ages of me, John, and Jane, then the result of this is going to be a left with the error message, the age of John is unknown. This is executed sequentially. The first one that fails, which is the second line in the for-comprehension, that one's going to return a left. And on left, map and flat map have no effect, so that thing just stays in there, and that's going to be the final result of this for-comprehension. But as we've seen, options are often wrapped in futures, and the same thing is true for eiters. Eiters come in futures as well. So let's change our age calculating method. Maybe it's going to look in a database for this. So it doesn't just return an either string or int, but it's going to return a future of a string or int. Then our method looks like this. And you can guess where we use the option transformer to work with a structure that looked like future option inner value. If we have a future either inner value, we're going to need the either transformer. Scala Z also provides an either transformer. So very similar to how this for-comprehension looked with option t in an earlier example. We can use either t to make a for-comprehension for this scenario. And it's interesting to see how this would look if you don't have a for-comprehension, if you don't have the monad transformer, but just try to make this program with map and flat map. It's going to be pretty terrible. And this way it just looks pretty clean, how it looks and what it does. But these are still simple cases because we invoke age 3 times and age returns the same structure every time. So it's really easy to figure out what's the structure that we should be working with, because we get a future either, so we need an either transformer to make it a single thing. But in practice, we often have methods that return different things. So for example, get A might return a future option int, get B is synchronous, returns an option int, and get C always returns a value but asynchronous, so it's in the future. And now we're in trouble again, because we cannot just use a for-comprehension, because every generator, so that's the things that are on the right side of the arrows, must have the same shape. You may have experienced you cannot use option and list in the same for-comprehension, or option and future, and the same thing here. Everything on the right side needs to have the same shape. So this also doesn't work. We cannot just put an option transformer around this, because most of them are not the right shape. So what do? The solution is simple. We basically figure out what's the shape that we want to have, and we convert every value into that same shape. So here we have a future with an either string or int. well, that's a pretty rich structure. It's asynchronous, and it can contain errors. We also have an option and an int. That's not a very rich structure. It's just an optional value. Future int, also not very rich. It's asynchronous, but nothing for error handling or missing values. So from these three, the most rich structure is the first one. It contains, the most amount of data. So what we can try to do here is get every value into the same shape, get every value into this future string or value shape. So that is what we do here. Get A is already the right shape. So if you look in the for comprehension, we can just put that in the either transformer and we don't have to do anything else. Get B is not in the right shape because it's an option. So we need to do two things. We need to upgrade the option to an either. And we do that using this / bigger than method. Yeah, that's annoying. I think there's also a regular named one, but I don't know what it's called. You'll get used to this. You can imagine if the value is there, if this is a sum, then it's easy. Then we just change it to a right. But if this option is a none, then we're lacking data because we want to transform it into something that does contain an error message. But if it's none, then we don't have an error message. So then in this case, we need to add this piece of data. What should be the error message if this get B returns a none? So that's what we do with this method. It just upgrades an option to an either, and we do that by supplying the left value for the case that this option is a none. And in C, and then we need to wrap it in a future because the shape that we use is future either. And for C, it's easier because C always has a value. There's always an integer in this future, so we can just make a right out of that. But we have to map the future to actually get this in the proper shape. Of course, there's another alternative. Sometimes you might have a very rich structure, but you say, I'm not really interested in the error messages. I just want the value. And if it doesn't work, then I'll just crash or whatever. Then you can also do the opposite. You could also decide to say, well, this future string or int, I'm going to downgrade that to an option. Either has a method to option that just throws away the left side. So if it's a left, then the result is going to be none. And if it's a right, then the result is going to be a sum with that value. And any error message that was available in the left side is just dropped. That's also useful. But the most important thing, you have to get it into the same shape. So, part 4, let's apply this in the play framework and see some tips and tricks if you're working with these for comprehensions with monad transformers. From my experience, this is a very, very useful structure in a play application. This is a future with an either inside. The left side is a result, and the right side is the value that you're working with. In play, a result means an HTTP result. So every request that play gets, you have to give play back a result. And play works asynchronously, so you can give back a future of a result. So if something goes wrong, we still have to generate a result, like a forbidden or bad request or internal server error, not found, whatever. So this is a very useful shape. And again, the most tricky thing is if we use this, then the most tricky thing is just getting all these kind of values that we have in our play application, get them into this shape. So we can make an object that has the same name, HTTP result, with a whole bunch of methods to get stuff into this shape. So the first one, apply, just takes a thing that's already the right shape, future result or A, and just puts it in the either transformer. But there's a whole bunch of methods that you can create for basically every kind of structure that you see in your application. Transform it in such a way that it fits in the structure of an either transformer with a future with an either inside. And then the final thing is at the end of our action method, which is the method where we get an HTTP request and we have to return a result, we need to give play a future of a result. Play doesn't really like my type HTTP result, which is an either transformer with grep. It just wants a future of a result, and that's what it's going to serve back to the client. So we can also make an implicit class, rich HTTP result, that takes an HTTP result, which is our container type, and the successful value should also be result. And then we transform that into a regular future result. What we do here is r.run. So r is the monad transformer, the either t. .run gives us the future of the either. And in this case, this is the last step in the action. Both the left side, if something went wrong, we put a result in there. And of course, the successful value that we want to give to play should also be a result, because we just have to give a result. So then we have an either of a result or a result. And for those cases, either has a merge method to say, well, if it's either a result or result, you can also just give me a result instead of this either class. So that's what the merge method does. And that's how we can get from an HTTP result to a future of a result. So how would this look in practice? Suppose that we make an action method show posts. That's an asynchronous method, which means that we have to give back a future of a result to play, and it takes some JSON data from the request. And the steps we want to do is we want to validate that the JSON in the body is a valid query object. For example, I just made that up. So in the first line in the for comprehension, to the right we do request.body.validate query. Validate is a method in the JSON part of play that's going to give us a JS result, which is isomorphic to an either, because it contains either an error or it contains a successful value. So suppose that on our HTTP result object, where we had all the methods to create the proper structure, we can add a method from JS result that just looks at the JS result and says, if it's a successful JS result, then we create a successful HTTP result, and if it failed, then we generate some bad request response or whatever. Once we have the query, we can put it into the find user method. That's some method on the service thing, whatever. That's going to give us a user back. We have to use some method on HTTP result to get that into the right shape, and then we get the posts for this user ID, and we have to get that in the right shape. And once we've done that, we can just put it in a for comprehension and generate our final result, which is a JSON representation of the posts from the database. So when I write play applications, then very regularly a play action is just a single for comprehension that looks pretty close to this. A single for comprehension that we just run in the end, and that generates our response. Now, we can make this slightly nicer with this one weird trick. That's also in Scala Z. There's a function application operator. So x1 is a method, or twice is a method, takes an integer, returns it doubled. So x1 we apply twice to the value 21, but we can also write it like we do in the bottom line, 21 weird method twice. And that's very interesting to just switch the order at which you see things once you look at it. So if we slightly modify the methods on our HTTP result object, on the object where we put everything in the right shape, then we could rewrite the show posts play action into this. And I like this better already, because now it's much more aligned what we actually want to do. We get the query by doing request.body_validate the query object, and then somewhere to the right of that we get it into the right shape. We figure out that an error is there. Oh, that's in the second line. Second line, we get the user by doing find user query. And once we have that, we apply this method from future option, to which we supply the error message if something went wrong. And then we get the posts, and then we modify that into the proper structure. And then finally we can generate our result, the OK JSON to JSON posts. And this looks not super nice on the slide, because it's pretty narrow. And I like really white lines in my editor. But if you just let it go off screen, then you can format it like this. And it looks even cuter. You just have very close together. What are you doing? It's very sequential. You can really see the steps in which this is going to happen. What I also like is that the error for a specific failure is on the same line as where that's occurring. While if you do map and flat map, then basically the most outer map or flat map, you have the map at the top, and then totally at the bottom, after indenting and de-indenting into a big V, you do some get or else, and there's the error. So the error and the thing that you're doing are not very localized when you use map and flat map, but here they're very neatly together. Well, if you want to do this, then some small tricks. You can use something like this. Just assign something. Just anywhere inside the for-comprehension that will just work, except it cannot be the first line, but everywhere else it will work. And just use underscore to discard the value. So this is basically how you can debug while you're in a for-comprehension to see intermediate values. Something else that you can do is, well, create a bit more interesting methods to construct either transformer values. We can say point, which basically takes a pure value and puts it into this entire structure. We can do fail and take an error, which creates a failure variant of our either transformer. So that means that we have a future with an either inside, and the either is a left, which contains an error. And then we can make some sort of control structures like require that takes a Boolean predicate and an error message, and we check the predicate. If it's true, then we create a successful value, but we don't really have any successful value, so we just put unit in it. Or we fail with the error. And then you can make programs like this in your for-comprehension. You can say A is, well, get A, put it into the right shape, and then basically check something from A. Check if A is bigger than 10. If it's not, then this is going to result in an either with a future with a left inside, so everything else is not going to happen. So this is some way to abort the computation. So what is not to like? Well, you've probably already identified most of the stuff that's not to like. Lifting everything into the proper container is pretty annoying. It's doable if you stick to similarly shaped containers. If I have this HTTP result type, I use it everywhere in the Play application, so I basically have 30 different methods to get every kind of thing into this shape. So it's not horrible, but it's annoying. It just messes with your screen space. The effects are ordered, which is sometimes annoying. You can imagine that sometimes in your mind it doesn't really matter whether you have a future with an option inside or an option with a future inside, but for this stuff it matters. It needs to be in one specific order, and that means that you have, if you have these containers in different orders, that you really have to modify them a lot to get them into the proper order. Sometimes the error messages that you get from the compiler are awkward. If you make an error in the fifth line of a for-comprehension, and sometimes the compiler says that there's something wrong with the first line, etc. And there are some weird cases with the irrefutable types. Basically, if the compiler cannot see that the thing you put left of an arrow in a for-comprehension is of the same type as the thing on the right. So if it knows that, then it says, oh, it's an irrefutable type. I'm certain that this is true. If it's not sure about that, then it's going to generate with filter calls in your desugared for-comprehension, in your map flat map thing. And that's annoying, because that's usually not what you want. And in some cases, filter is not easy to implement. For example, if you have an either, that means you have either an error or a successful value. You cannot just do filter on it, because what would filter do? On an option is easy. If you have a sum and the filter fails, then you end up with a none. But if you have a right with some value in it, and you would do filter and it fails, then you need to come up with some left value, which you don't have. So that is awkward. Although in Scala Z there's some stuff around that I don't want to get into now. In my opinion, this is very useful, and you can use it. It's awkward sometimes, it's annoying sometimes, but it is, I think, a pretty nice solution to working with deep nesting problems that you have if you have futures with options or future with eithers. Just lift everything into the rich structure, and you can properly put the errors near stuff that goes wrong. You can see how your program will execute sequentially. Yeah, I like it. If you want to learn more about this, then I have this repository on Github that also links to a presentation that's slightly slower paced than this, and it contains tutorials that you can do. And I recommend just doing the presentation and then the tutorials, and then again in a week and again in a couple of weeks, and then, well, we'll probably be fine. So that's it. Questions? If there's any more questions after the talk, I'm usually at the Lunatech stand downstairs. We're also hiring, so if you want to work with us, then also find me. I'll be here all day and tomorrow. Yeah, questions? Yeah?
Hello. Why?
So the question is, why do I use either instead of the Scala try? That is because either is richer than try. Try can only contain exceptions. And for example, in my play example, I want my failure cases to be proper HTTP results and not exceptions because, for example, HTTP results, I can give a status, I can give a body, etc. Just what I want. And try doesn't do that. Also, try in Scala is not a monad. It does have map and flat map methods. What I didn't say is to be a proper monad, it does not only need to have these methods, but there's also some rules, some invariants that you should, that apply to things before they are monads, and try is not one of them.
Future fails the same test.
Future fails the same test, so don't use future. Use task from Scala Z. No. Thank you.
Thing in order to avoid that?
The question is, do I write my own monad transformer or do I pull in the dependency on Scala Z? The answer is, pulling in the dependency on Scala Z is basically the end goal. So I do that.
But don't you see that like as an issue? I mean, ask for that, like this is the thing, standard like.
No, I don't see it as an issue. I think it's a high-quality library, and it's very easy to just pick small parts of this. For example, you can just use the monad transformer, just use either, and not anything else, and you're going to be perfectly fine. No more questions?
Why do you think the standard library doesn't have a write bias?
So the question is, what's my opinion on the standard library not having a write biased either? Tony Morris wrote both the either in the Scala standard library and the either in Scala Z, and he thinks it's a huge mistake that the either in the Scala standard library is not write biased. I don't really mind. I just don't use it that often, but yeah.
If you write your own either transformer, you can make it write biased, right?
So the question is, if you make your own either transformer, you can make it write biased. Yeah, I guess so. It's actually also pretty easy to make a pimp my library style enhancement to the Scala either, I think, and just add map and flat map. That also works then. It suddenly becomes sort of a monad. No more questions? Then thanks again.